You are welcome to my YouTube channel. Our topic for today is the complex number system. We shall begin with our definition. A complex number is any number of the form a plus bi, where a and b are real numbers and I squared is equal to minus 1. The set of all complex numbers is usually defined by the letter C, such that Z will be equal to a plus bi, where a and b is in R. This is how we define it mathematically. It is important to know that every real number x can be expressed in the form of a complex number. It follows that the set of real numbers is a subset of the set of complex numbers. Note that when performing arithmetic with complex numbers, we should keep the following facts in mind. Firstly, the rules of arithmetic that are valid for real numbers are also valid for complex numbers. Secondly, I squared is equal to minus 1. And higher powers of I can occur, such as I cube is equal to minus I raised to the power 4 is equal to 1, I raised to the power 5 is equal to I, and so on and so forth. Our next subtopic here is the graphical representation of complex numbers. We use what is called the Argand diagram to represent complex numbers. A typical example is on the screen, where we have to represent the complex number z equal to 2 plus 3i. You will quickly know that the real part is represented on the y-axis, while the imaginary part is located or drawn from the y-axis. Now, we can use the Argand diagram to add complex numbers, subtract complex numbers, and do other basic mathematical operations. An example is what we have here. We try to add z1 to z2. When assuming z1 is 3 plus 2i and z2 is 1 plus 3i, then z1 plus z2 is what you're seeing on the screen being described. Basically, we use what is called the parallelogram law to find either addition or subtraction of complex numbers. Let's look at another example. In this case, we have three complex numbers, z1, z2, and z3. z1 is equal to 4 plus 2i, z2 is equal to minus 2 plus 3i, and z3 equal to minus 1 plus 6i. We are to determine z1 plus z2 minus z3 on an Argand diagram. Solution. Let OA equal to z1 and OB equal to z2, while OC is minus z3, OP is z1 plus z2, OQ is z1 plus z2 minus z3, which is the solution we are looking for. Now let's represent it on the Argand diagram. This is how it will look like. Summing z1 plus z2 minus z3. If you apply your parallelogram law properly, you will discover that our solution will be Q, 0Q. That is where we have z1 plus z2 minus z3. Since z is equal to a plus bi, we can actually write a complex number into what is called a polar form. And how is this polar form written? It is written as z equal to r cos theta plus I r sine theta. Then when you factor the r out, you have r equal to r cos theta plus I sine theta. Okay, where the r is called the modulus of the complex number z and is often abbreviated to mod z, or indicated by the notation modulus of z. Theta is called the argument of the complex number z and is abbreviated as argz. Let's take some examples. Express the following complex numbers in polar form. I, z equal to 7 plus 2i, I, z equal to 3 minus I, z equal to minus 4 plus 6i. Solution. If z is equal to 7 plus 2i, the modulus of z is square root of 53 and the argument of z is 15.95 degrees. Now, the polar form will now be z equal to 7.28 in bracket cos 15.95 degrees plus I sine 15.95 degrees. That is how polar form is being represented. Solution to II. If z is 3 minus I, the modulus is square root of 5. And since z lies in the fourth quadrant, why is it on the fourth quadrant? Because the real part 3 is positive and the imaginary part is negative. So where we have x positive, y negative is on the fourth quadrant. So in that case, you say the theta will be 360 degrees minus the arctan of 1 over 3. And you're going to get 341.57 degrees. So the polar form will be written as z equal to 2.24 in bracket cos 341.57 degrees plus sine 341.57 degrees. I, solution to I, if z equal to minus 4 plus 6i, the modulus of z is 7.21, and here z lies in the second quadrant, so the theta will be 180 degrees minus arctan 6 over 4, and that will give us 123.69 degrees. In polar form, it will be written as z equal to 7.21 cosine 123.69 degrees plus I sine 123.69 degrees. Our next subtopic is the Mohs theorem. Suppose that z is equal to r cos theta plus I sine theta, then the Mohs theorem says that z square is equal to r square cos 2 theta plus I sine 2 theta. Similarly, the Mohs theorem says also that z raised to power 3 will give us r raised to power 3 cos 3 theta plus I sine 3 theta. Therefore, in general, r cos theta plus I sine theta raised to power n will give us r raised to power n cos n theta plus I sine n theta. This is what we call the De Mohs theorem. Application of De Mohs theorem. Some examples. Let's find z raised to power 1 over 2 if z is equal to 4 cos 70 degrees plus I sine 70 degrees. Solution. If z is equal to 4 cos 70 degrees plus I sine 70 degrees, then z raised to power 1 over 2, where our n in this case is 1 over 2. When you apply the Mohs theorem properly, you are going to get 2 cosine 35 degrees plus I sine 35 degrees. Note here that our n is 1 over 2. This theorem works for any number at all, whether positive numbers, negative numbers, whole numbers, or fractions. Let's look at any truths of unity. Consider the complex number z, which is equal to 8 cosine 120 degrees plus I sine 120 degrees. Note here that 360 degrees equals 1 revolution, so adding 120 degrees to any number of revolutions leave OZ in the same position. That is, Z is equal to 8 cos 120 degrees plus I sine 120 degrees, or by the time you add 360 to each of those components of sine and cosine, and sine and cosine. Yes, you're going to have sine 120 degrees cos 4 cos 120 cos 480 cos 840 and so on and so forth, simply by adding 360 degrees. Now if we simplify by applying the Mohs theorem to each of these, we are going to get that z raised to power 1 over 3 is going to give us 2 cos 40 plus I sine 40, or 2 cos 160 plus I sine 160, and so on and so forth. Let's look at this example. We should find all the fifth roots of square root of 32 cosine 315 degrees plus I sine 315 degrees. Solution. Note that square root of 32 cosine 315 degree plus I sine 315 degrees is equal to square root of 32 cosine 315 degrees plus k 360 degrees. So that is the revolution there, the 360 degrees k. Okay, where k is any integer including 0. Now using the Mohs theorem, the fifth root of square root of 32 cosine 315 plus I sine 315 will be given as what we have on the screen, raised to power 1 over 5. So 1/5 of square root of 32 in bracket cosine 315 degrees plus k 360 degrees divided by 5, and sine 315 degrees plus k 360 degrees divided by 5. When you do a proper simplification, you're going to have square root of 2 cos 63 degrees plus k 72 degrees plus I sine 63 degrees plus k 72 degrees. Assigning the values k going from 0 to 4, since you're on the fifth root, so you start with 0 to 4. Now we have that when k is 0, we are going to have our z1. When k is 1, we have our z2. When k is 2, we have our z3. And when k is 3, we have our z4. And when k is 4, we have our z5. Thus, the 5 fifth roots are obtained by assigning 0, 1, 2, 3, 4 to k. Thank you.